All right, everyone. Welcome back to Conceptual Physics. Today we're going to be talking about acceleration. And there's many ways that you can be thinking about acceleration and probably already you already have preconceived notions of what acceleration is. But in physics, I think the best and simplest way to think about acceleration is the change in an object's motion. So yes, acceleration is if something is getting faster and faster, it's accelerating. That is correct because it's changing its motion. However, it's a few other things. If it's slowing down, an object has an acceleration as well. Or if you are changing direction, changing its motion, you are also accelerating. So anything that's changing in motion, slowing down, speeding up, turning, anything like that is acceleration. Okay, so let's go more into nitty gritty. Acceleration is a change in the velocity of an object. And this should make sense. How much acceleration something else is how much the object's velocity is changing. Velocity meaning it could also be changing direction over what period of time. Okay, so the shorter the period of time, the more the acceleration. The more the object is changing its velocity, the more the acceleration. Okay, if it changes time in a shorter amount of time, there's more acceleration. If it changes time in a longer amount of time, less acceleration. Okay, so this is how we're going to see the formula. Actually, we're going to see this more. Again, this triangle over here represents change in. So we're just doing the final velocity versus the initial velocity. Okay. So an example that we often hear about, especially if you're into cars or something like that, it'll say something like, this car can go from 0 to 60 in 5.3 seconds. So that's just showing, how fast an object is changing its speed and therefore accelerating. So it's changing its speed from 0 to 60. Okay, so that's the change in velocity part, and it's changing it in 5.3 seconds. Okay, so that's a little bit of an example of acceleration that we might have heard of, probably in a car commercial or something like that. And if not, listen to the next car commercial. Okay, so units used for acceleration. So remember, acceleration is the change in velocity divided by time. So an example you might see, you probably won't see this too much, but a unit of time could be miles per hour and seconds. Okay. So it might look like this: miles per hour per second, which looks strange, but that's how acceleration is. There's a unit of speed, in this case is miles per hour, and then there's a unit of time under it, or in the denominator. You won't see those kind of units that much, but it is a unit of acceleration. But let's see, a car goes from 0 to 60 miles an hour in 6 seconds. It would look something like this: 60 miles an hour, it took 6 seconds, so it converts to 10 mile an hour per second. Every second, the car is getting 10 miles an hour faster. Okay. Okay, so this is the most used acceleration. This is what you can see most of the time. Is the unit of speed to be meters per second, which we've seen a lot with speed and velocity, and over seconds. Okay, meters per second over second. And I know this looks like strange because it's like meters per second squared. However, I just want you to think about it. If something is going, let's say, 5 meters per second, what that means is every second it's getting 5 meters per second faster. Okay, or it's changing its speed or changing its velocity by 5 meters per second every second. Okay, we'll do more examples with this, so it'll probably make more sense. So it's fine if you're confused right now. Okay, which of the following scenarios is not an example of acceleration? Again, pause the video if you want to take your time. Okay. These are the two examples of no acceleration. Cruising at 100 miles an hour. Yes, you are going very fast. And a lot of times people mix up fastness with acceleration. But actually, how fast or slow you're going has really nothing to do with acceleration. It's the changing of the speed or changing of the velocity. So, cruising at 100 miles an hour, not changing your speed, isn't going to do anything. being at rest, again, you're not changing your velocity at all. You're being at the same nothing speed. So that's not going to do anything. So a horse gallops with a constant acceleration of 3 meters per second squared. Which statement below is true? A, the horse velocity does not change. B, the horse moves 3 meters every second. C, the horse's velocity increases 3 meters every second. D, the horse's velocity increases 3 meters per second every second. Okay, so this would be D. And again, I know we already talked about this, but we're just learning this, so I just want to go over it. This means the horse, I'm going to draw a box here, at first it's not moving. But then 1 second later, it's going to be going a bit faster. It's going to be going 3 meters per second. The next second, it's going to be going faster. It's going to be going 6 meters per second. The next second, it's going to be going faster. It's going to be going 9 meters per second. Okay, and so on and so forth. So every 3 meters per second squared means every second the velocity is changing by 3 meters per second. Okay, oftentimes it's increasing its speed, but definitely not always. Okay, let's look at this next slide. If a dog has an acceleration of 5 meters per second squared and it starts running from rest, what will its velocity be after 3 seconds? So again, we can do the math for this kind of problem, and the math isn't too difficult. However, let's just right now, let's just try to think about it. Okay, just maybe try to do the math in our head and think about what this means. So remember, 5 meters per second squared means every second it's getting 5 meters per second faster. Especially if it's starting from rest, it starts from 0 and gets faster and faster. So we're just going to be doing 5 times 3 in this case. So it's going from 0 to 5, 5 to 10, 10 to 15. Okay, so it's going to be 15 meters per second. Okay, so this one's a little bit different. A fast cow is moving with the speed of 10 meters per second. It starts slowing down with an acceleration of 3 meters per second squared. What will its velocity be after 2 seconds? Okay, so this one's a little bit different. Again, you could do the math of it all, but right now I'm just trying to think about it conceptually. So at first, it's going at 10 meters per second. Then we should know its acceleration is 3 meters per second squared, but it's slowing down. So what this should mean is after the next second, I'm going to say t equals 1 second, it should be 3 meters per second slower. So this should be 7 meters per second. And then after the next second 2, which we're looking for, it should be another 3 down. So that should be 4 meters per second. Okay. So that should be the answer right there. I hope that makes sense. Again, we're going to be doing this like more mathematically later on. So if this isn't making sense, maybe the math part will make a little bit more sense, which you can do as well to answer these questions. Okay. Which of the following statements will have the largest amount of acceleration? An object that has a large change in velocity with a long period of time, B, a small change in velocity with a short period of time, C, a large change in velocity with a short period of time, D, a small change in velocity within a long period of time. So remember, acceleration is equal to the change in velocity over time. So what would be optimal to make this acceleration be the highest that it can be would be if this change in velocity is going up or is very high, and this time is very low. Okay, so it's going to be option C. Which scenario has a larger acceleration? A car that goes from 0 to 20 miles an hour in 3 seconds. B, a car that goes from 30 to 40 miles an hour in 4 seconds. C, a car that is cruising at 100 miles an hour. Okay, so we should know right away, yes, C is going the fastest. So you might be tempted to write that. However, it's cruising, meaning it's not changing in velocity. So again, we don't care about how fast something is going with acceleration. We only care about how much it's changing its velocity. So if it's not changing it, that means this is just equal to 0, and it does not have a large acceleration. Part B, you might be tempted like, 30 miles an hour and 40 miles an hour are bigger numbers than 0 and 20. So that should mean that they are going, that's going to have more acceleration. But no, part A has a larger change in velocity. It has a change in velocity of 20 miles an hour, while part B only has a change in velocity of 10. Okay. And part A has a shorter time, 3 seconds, while part B has a longer period of time. Okay. So it is going to be A. Okay. Okay. First math example for this kind of topic, acceleration. A crazy llama is jogging at 12 meters per second when it sees a mouse behind her. The llama starts to panic and reaches a speed of 18 meters per second in 1.3 seconds. What is the acceleration of the llama? Okay, very good. So, doing problems like this, again, I would very much suggest just kind of writing all these different things out. So, first, it starts out at a speed of 12 meters per second. So, I'm going to say the initial velocity is 12 meters per second when it sees a mouse behind it. The llama starts to panic and reaches a speed of 18 meters per second in 1.3 seconds. So, I'm going to say the final speed is going to be 18 meters per second, and it took the llama a time of 1.3 seconds. What is acceleration? So now that I wrote down the variables, I'm going to be writing down what we're looking for. Okay. Next, also, I'd kind of draw this picture out. Let me see what a drawing would be. So I'm going to say it's like going like this. 12 meters per second. And then I'm going to kind of draw it sometime in the near future. Going faster. Maybe I'll do it like this. However you want to do it. Okay. And this took a elapsed time of 1.3 seconds. Anyway, it's very important to just organize your information like this. Okay, now that you did that, I would also be looking at what formula you're going to use. And so far with the acceleration, we only have one formula. Acceleration is equal to a change in velocity, v final minus v initial, divided by time. Okay, so now let's just plug things in. And this is a relatively easy problem, so you might be like, oh, I don't want to draw it, I don't want to do all this kind of stuff. And, that's fine, but you are going to make a lot more mistakes by doing that. So I would very much get in the habit of, even no matter how easy it is, to just take the steps of making it easy, of doing all the work, okay? It is going to definitely save you with a lot of little mistakes and stuff like that. Okay, so let's just do 18 minus 12 divided by 1.3, and we get 4.62-ish meters per second squared. Okay. Next example. A car starts from rest and reaches a speed of 40 meters per second in 2.4 seconds. What is the acceleration of the car? Okay, keywords. Starts from rest, reaches a speed of 40 meters per second in 2.4 seconds. What is the acceleration of the car? Okay, so let's see. Starts from rest, meaning the initial velocity is 0, reaches speed of 40 meters per second, which means final speed is 40 meters per second, and the time it took is 2.4 seconds. What is the acceleration? We're looking for the acceleration. Great. Acceleration is equal to v final minus v initial divided by time. Now let's just plug things in. 40 minus 0 divided by 2.4. And let's do this. 16.67. Okay, great. Okay. Again, this just meaning that every second it's getting 16.67 meters per second faster. Okay, next example problem here. A car starts going 30 meters per second east. The driver suddenly sees a baby squirrel and slams on her brakes, coming to a stop in 0.9 seconds. What acceleration does the car experience? Okay, so let's look at this. What we should know is the car is initially going 30 meters per second. Okay, slams on her brakes. Oh, I should do this. Comes to a stop, 0.9 seconds, acceleration. Okay, I'm going to say the time is equal to 0.9 seconds. And you might be thinking, okay, where is the other variable? And with these kind of problems, we always need to have three variables before we can solve for the fourth. So we have to find three variables that we know. And we should know comes to a stop tells us that the final velocity is actually 0. Okay, and now this will help us find the fourth variable, which is acceleration. But yeah, always know with these kind of problems, you need to be finding, with the acceleration, you need to be finding the three known variables first. So acceleration is equal to the final velocity minus the initial velocity divided by time. And now we have 0, because that's the final, minus 30 divided by 0.9. Okay. And what's the acceleration? Negative 30 divided by 0.9. And we get negative 33.33 meters per second squared. Or we could do 33.33 meters per second squared west. Okay, and something important that's going on here. So this car is originally going 30 meters per second east. This is the velocity. However, if something is slowing down or coming to a stop, like this problem is here, that means the acceleration is going to be in the opposite direction. Okay, the acceleration is going to be in the opposite direction whenever something's slowing down. If it's speeding up, the acceleration would be in the positive direction. But since this one is slowing down, it's going in the opposite direction. So that's why this acceleration is negative here, is because it's going to the left. Okay, or going west in this situation. All right, let's look at the next problem. In which scenarios does the car speed increase/decrease? In which scenarios does the car have a negative acceleration? Okay, so take a moment to pause if you want to, and let's see how we do this. Okay, so first of all, let's look at speed increase and decrease. So again, like I mentioned, whenever the acceleration and the velocity are in the same direction, that means the speed is increasing. So I'm going to do A here, increase. I'm going to first say A is increasing. We can see, I'm going to say decrease. We can see for part B over here, acceleration and velocity are going in opposite directions, meaning this one is moving to the right because that's where the velocity is, but it's slowing down to the left. So this is going to be B. Okay. Okay, C again is moving to the left. However, it's slowing down because acceleration is in the opposite direction. So this is also decreasing. D is moving to the left, and it's getting faster and faster going to the left because they are in the same direction. So this is D. Okay. Part B. In what scenario does the car have negative acceleration? Okay. So you might be thinking, okay, if it's slowing down, it must have a negative acceleration. And that'd be, a valid way to solve this problem, but that's not exactly true. The only way we know if something has a negative acceleration or not, and what we're going to do, is if it is going to the left. So B is going to the left, and D is going to the left, and that's why both of those are going to have negative acceleration because it's going to the left. And again, it has nothing to do with slowing down or speeding up. It just has to do with the direction of the vector or the direction of the acceleration. Okay. All right, so manipulating formulas. This is the main formula that we've been using so far. Acceleration is equal to the final velocity minus the initial velocity over time. I just want you to know, doing some algebra, which you guys might know but might be a little rusty on, you can manipulate this to find our other variables like time, final velocity, and initial velocity. I guess I'll show how to do it one way, and then just know that you can change it in other kind of ways. So you might have to memorize this, or you might have a formula sheet. So if we want to find time instead of acceleration, what we can do is we can multiply both sides by time. What would happen is we get rid of this time, and then we have time on this side. And then we can get rid of acceleration by dividing both sides by acceleration. And then we get this formula here. Time is equal to the final velocity minus the initial velocity divided by a. Okay, and you could do all these different kind of algebraic manipulations to find these other variables. So either know how to do that, memorize it, or if your teacher allows, have the formula sheet. Okay, next example. All right, so let's look at this example. A ball is rolling at a rate of 5 meters per second. It starts to go down a small slide, and the ball experiences an acceleration of 3.8 meters per second squared. What will the object's speed be after 1.4 seconds? Before I start, and I should have probably talked about this earlier, is that a lot of times students mix up, oh, what's the variable of speed and what's the variable of acceleration? Just know that if you're seeing any of these like seconds squared kind of thing, that shows that um, that value is a unit of acceleration. Okay, so that's one helpful thing. So let's start writing some things down that we know. The initial velocity is 5 meters per second. The acceleration is 3.8 meters per second squared, and the time is equal to 1.4 seconds. We're looking for what the speed of the object is after 1.4 seconds. So the final velocity, that's what we're looking for. Okay, so we should know the formula. Acceleration is equal to the final velocity minus the initial velocity over time. And what we're looking for in this scenario is the final velocity. Okay, so we're going to manipulate this formula in order to find that. So first, I'm just going to multiply both sides by time. And then this time cancels out over here. So we have acceleration times time is equal to final velocity minus initial velocity. And then I'm going to add initial velocity on both sides. And then we should have acceleration on time plus initial velocity is equal to final velocity. Okay, and again, this is what our formula should look like from our last slide. Final velocity is equal to initial velocity plus AT, acceleration times time. Okay, and that's what we get here. So now that we manipulated it, again, if you just want to memorize it, you can, or whatever your teacher allows. So final velocity, that's what we're looking for. Initial velocity is 5 plus the acceleration, which is 3.8 times time, which is 1.4. And now we could just plug this into our calculator. I'm going to start with the 3.8 side. 3.8 times 1.4 plus 5 equals 10.32 meters per second. All right. All right, guys, let's look at the next problem. A bike is driving at a speed of 14 meters per second. The biker notices there is a donkey up ahead and slams on the brakes. If the brakes apply an acceleration of 3.2 meters per second squared, how much time will it take for the bike to stop? Okay, so let's look at this. The initial velocity, this one is a little bit tricky, but hopefully you guys can figure it out, and definitely pause it to figure it out. Initial velocity is 14 meters per second. It slams on the brakes. So what we need to do is, it's not giving the direction, but I'm assuming that it's first starting out just going to the right. If you have it as negative 14, that's fine. But what we do need is it's slamming on the brakes, so it's slowing down. So the acceleration has to be going in the opposite direction as the velocity. Okay. So if you have the initial velocity as negative, acceleration should be positive. But if you have it as positive, which most of you guys probably do, the acceleration should be negative. And then we should know it comes to a stop. So the final velocity is equal to 0. And what we're looking for is time. Okay. Now we have acceleration is equal to final velocity minus initial velocity over time. And we're looking for time, so we have to somehow figure this out. To me, the simplest way of how I see doing this is bringing the time over to the other side. So I'm going to do times t and times t over here. So we have time times acceleration is equal to final velocity minus initial velocity. And then I'm going to divide both sides by a. So then I have time is equal to final velocity minus initial velocity over a. Okay, and now we could solve for time. And this is the same formula from before right here. Okay, so if you just want to memorize that or whatever, you have that option. Okay, now let's start plugging things in. Time is equal to final velocity, 0, minus initial velocity, 14, divided by the acceleration, negative 3.2. And let's see what we get. Negative 14 divided by negative 3.2, 4.375. Okay, 4.375 seconds. All right, I believe this is the last one. Let's see how it goes. A mama lion is jogging along when she finally sees her cub. The mama starts to accelerate toward her cub at a rate of 0.8 meters per second squared. The mama takes 4.2 seconds, reaching her cub at a speed of 8 meters per second. With what speed was the mama jogging with before she saw her cub? Okay, let's see. Let me underline key things. Okay, so we have the acceleration 0.8 meters per second squared. We have the time 4.2 seconds, reaching her at a speed of 8 meters per second. With what speed was Mama jogging before she saw her cub? So she reaches her, meaning the final velocity is going to be 8 meters per second. And we're looking for what did she start out with. So that's the initial velocity. Okay. Now we know the formula for acceleration, v final minus v initial divided by time. And this time we're looking for the initial velocity. So again, I'm going to multiply both sides by time. Acceleration times time is equal to v final minus v initial. And then I'm going to subtract both sides by v initial. And then I have acceleration times time minus v initial is equal to... sorry. No, we're looking for v initial. We shouldn't be subtracting it. Sorry. All right. We're looking for v final. No, we're looking for v initial. Sorry, my fault. We're subtracting v final from both sides. So we have acceleration times time minus v final is equal to negative v initial. Okay. I don't like this negative, so I am going to multiply each side by -1. This cancels out the negative on this side, but then it changes everything else. So we have negative acceleration times time plus v final is equal to v initial. And this is the same formula. It looks a little bit different than this one, but it's the same formula as this. Okay. So the order is different, but it's the same formula. So let's now put things in. So negative acceleration, or maybe I'm just going to rearrange this. V initial is equal to negative acceleration times time plus v final. So negative, the acceleration is 0.8 times time, which is 4.2, plus the final velocity, which is 8. And let's see what we get. Negative 0.8 times 4.2 plus 8 gives us 4.64 meters per second. All right, and I think that's pretty much for acceleration as of now. So next time we're going to be talking about free fall. So I hope you guys are excited for that. And I'll catch you with the next one. Thanks for watching, everyone.